Hello everyone, and today I'm going to show you how to solve the problem subsets in Python using recursive backtracking. We are given an integer array nums of unique elements, and we want to return all the possible subsets, which is essentially the power set. So the solution set must not contain duplicate subsets, and we want to return the solution in any order. So for example, if we have nums as 1, 2, 3, we basically have the empty set 1, 2, the set 1, 2, 3, 1, 3, 2, 3, and 1, 2, 3. Notice that the empty sets and the original set is also included. In example 2, we have, and then all subsets of the set containing 0 is going to be the empty set and the set containing 0. So if you notice some sort of pattern, then the power set will basically contain 2 to the length of the numbers elements. So let's say this set has 3 elements, then the power set will contain 8 sets actually, which is all possible subsets. Now, I think it's very important to understand the terminology behind the subset. So let's say A is a set. If you have taken an advanced mathematics course, you may have seen that this is Russell's paradox, but particularly in this case, a set is going to be a collection of distinct objects. So that is basically going to be it for understanding what the set is. A subset is basically a set that contains some of the elements of the set here. So let's say B is a set and we want, let's say 1, 2 as a subset. We can say that B is a subset of A, and the notation for subset is basically this C and then with a line under it, an A. Now what about C is here? We got 1, 4 this time. Notice that 4 is not an A, so immediately this makes it not a subset. So in order to write the symbol for not a subset, we basically write the subset symbol and then we cross this out. But I think now we should understand what subsets are, and we want to understand how we can get all possible subsets using recursive backtracking. Now particularly, the form of prerequisite, of course, is recursion, and you should also know about trees because for the essence of almost all these backtracking problems, you will be relying heavily on tree data structures. So I think it's very important that we have this here. So here's how we're going to start off here. So let's say we have an empty list. This empty list will basically contain our solution here. And this will just be a temporary solution. If you're familiar with backtracking, once you reach a dead end, you go back. Let's go ahead and understand how to pick all these elements here. So let's traverse through this. So this will be our pointer, 1, and particularly, we're going to be going through all these indices here. So we have 1. If you want to get all possible combinations, you will have to be a bit clever on this one. You can choose to add 1 to the set, or you can choose to avoid 1 in the set. So we're going to need to consider all possibilities. So let's go ahead with this first possibility here. So we can add 1 here. So, and particularly, I'm making this very large because we want to go ahead and make space for all arrays, essentially. So we have an option to add 1, and then we also have an option to not add 1. So x1, how will that impact our array? So if we add 1 to the set, we are stuck with 1, and then if we go right, then we're going to be keeping the set empty because we're skipping it. Now what we want to do is, and now what we basically want is go depth down here. So particularly this algorithm should go here, but as you see. Okay, so we basically want to be considering all the possibilities, but we are going to be doing it depth down first. So you will see me go depth down and basically explore all different types of sets one by one. In option 1, we have an option to add or remove it. Let's first consider the option to add 1 to the set, and then basically we add this to the set here. If we have 1, then we also have to consider this thing here too. So our pointer will be at 2. We have an option to add or not add it, essentially. So again, let's go ahead and add it. And now we basically have another recursive call. We can basically add 3 or we can not add it. So again, we will decide to add it, and this time we will go back here. So let's say we have 1, 2, 3. Now particularly, we are done with traversing this entire thing. So we are done with one iteration. We're done going depth down, and then we can go backtrack it. This is one of our base cases. And now let's go back to, let's say we have 3, and then we go into the other option from 1, 2. We have an option to not add 3, so this will basically remain the same. So that'll be 1, 2. And this basically exhausts 1, 2. We can basically go back here. We're going to go back to 1. So go back to this one right here. So that will be position 1. So that means we have number 2. The other option here is to not add 2. So this is what it's going to consist of. This will still be a set of 1. And particularly for this set, we want to increment this pointer, and we want to go ahead and obviously add or not add. We want to explore the add possibility first. So that's what we're going to do. So if we added 3, then 1, 3 is going to be a subset. But if we don't add 3, then we're basically going to have 1 as a subset. And that's basically going to be it for this left-hand side. We basically have it for this thing right here, because we run into our base case afterwards, and then we go back here. Since this is already done, we're going to go back, and this pointer is now at 2. And since we're done exploring all possibilities here, we can go back to the empty one. We can go ahead and explore the second option. So yeah, we can go ahead and not add it here. We can set our pointer back to 1, obviously, and then we can choose to not add 1, which will obviously keep the subset empty. So now comes the option to see if we can add 2 or remove 2. So we increment this pointer. Let's say we added 2. So if we added 2, then here's what this result set will contain. So we got 2, and then if we added 3, let's say here we added 3. So 2, 3 will be the set here. And that's pretty much vice versa. If we don't choose to add 3, then this will basically be the set here. In this empty set, we choose not to add 2, which is our second possibility, which will keep our set empty. And then we have an option to add 3 or not add 3. So if we add 3, then the result will basically be 3. And then if we don't add it, then the result will basically be empty. What is so special about doing this in the form of a tree? Now, doing this in the form of a tree is better because it allows us to investigate that the solutions are, in fact, leaves of the decision tree. So once we reach our base case, we can basically add this to our main result set. This is known as a partial solution. That's basically going to be it for this algorithm right here. So here's what we're actually going to do. So what do we actually do inside of this when we reach the leaves? So once we realize we have reached our base cases here and our traversal index is no longer in bounds, so this is where we know that we have reached our base case. And this is our only base case that we have so far. So yeah, what can we do to store this result here? So let's say we have some sort of result here and we want to sort of accumulate this here. Once we do this, we got 1, 2, 3, and then we got 1, 2, and then we got 1, 3, 1, and then 2, 3, 2, and then 3, and then the empty set. And that's basically going to be all the subsets here. I'm going to answer some questions that you may have, like why do we bump back the index? Well, it's because we are splitting each of these paths into 2 separate recursive calls. One for if we decide to include the current number, and 2 if we don't, then we basically have to call twice here. And either way, there'll still be recursive calls to this right here. Another question is basically, what do we do after adding this? And how do we know whether to go from adding to removing it? Basically, what we're going to do is append and recursively call this. And what we want to do is, similarly, you want to pop the latest number to go back to the parent node, essentially, and then 1, 2, and then essentially we're not going to add 2. So we recursively call 1, 2, and then with the next index here. And this is basically an example of what's going on here. So let's go ahead and actually transform this to code. Okay, now obviously we are not making an actual tree. Now the main reason is because it will be very time consuming and space consuming too. So, and in fact, we need our results as a list of lists. So we want to get the current length of the numbers. So, okay, nlen, that will be length of the numbers. So this will be good in case we want to keep track of something here. And now we have two arrays, two lists. We want one for the 2D list. The partial solution essentially is going to be the one-dimensional list. Now what we want to do is actually go ahead and do the recursive backtracking. We're going to make a method called backtrack, and then this will take in a current number or index as a parameter. So we're going to call this I. Okay, for our base case, we want to make sure that I is in bounds. Whichever one we're checking is in bounds. So if I is equivalent to nlen, then add the current solution to the results. So results.append, and then we have a copy of the solution, and then return. Now, it's a copy because we do not want to sort of modify this result list in the process. For the rest of our code, we are in this case now where the current index is in bounds. So here's what we want to do. We want to first of all add or skip. So that's what we want to do, add or skip. So first of all, when we want to add something to a set, we want to add the current number at the index to the partial solution. So append nums at index I, and then what we want to do is basically, now that we're done adding, you want to go ahead and make a recursive call. So we're going to call backtrack, and then add the index by 1. And this is really important. Make sure you don't do backtrack I inside backtrack I. Otherwise, you will be going into a Stack Overflow error most of the time. So that is basically it. Backtrack here. So this is basically another call here. If I is basically here, this goes step down until we reach a base case. After this function call reaches the base case, what we want to do is go into our next case where we want to essentially skip the element. But we do not want to keep the element here. So this is why we want to essentially pop the current element when we want to go back from the decision tree. And now when it comes to actually skipping the element, we want to go ahead and backtrack and then I plus 1. Make sure both of these are I plus 1 because we want every number to be observed here. And now basically what we want to do is basically go call this method. Don't forget to call the method at index 0 because 0 is the starting index in Python. And then if we want to return the current result, the result is going to be a two-dimensional list essentially. Since we are appending and popping, we are going to essentially be adding a copy here. So that is basically going to be it for this code here. Let's actually go ahead and run it. And there we go. We should be able to solve this. And there we go. So thank you guys very much for watching this video. If you guys enjoyed, make sure to leave a like and subscribe. Share this video with others in need. And of course, spread the word to help my channel reach a wider audience, and especially because I am planning to do some videos related to Python, data science, AI, and machine learning near in the future. So make sure you stay tuned for those videos as well. And of course, see you guys in another video. Peace out.